Hello, everyone. I'm glad to welcome you here. I hope you had a good contest today. I hope you like the problems. So today we will discuss the problems right now. Yeah, without further ado, let's start. So we'll go just left to right, I think. I mean, in order of problems. So problem A was the one that many people solved. Yeah, you had some minions. Each minion had two values, attack and buff, and you wanted to order them in some way so that when every minion buffs someone else with BI, the attacks AI are not increasing, non-increasing from left to right. So the question is whether we can order the minions. So first of all, yeah, let me also open the chat here. Yeah, first of all, the first case to analyze is n equal to 2, which is actually given in the examples. And when n equals to 2, we can always order the minions. The answer is always yes, just because we know every minion buffs the other one, so we know the final attacks of them. And the second case is harder, of course, when n is greater than 2. The actual question is like, how do we order? Can we actually know the ordering? And it turns out that we should just order them in order in decreasing order of AI. And if AIs are equal, then increasing order of BI. And this is the actual order that we should use. And now we should check if this order is good or not. And to check that, for each I from 1 to n minus 1, we should check if when all buffs go to AI to the next minion, will it actually beat the current minion? So we take AI plus 1 and we add the sum of all BI minus BI plus 1, because that's actually the amount of buffs the I plus first minion can get, right? The total of BI minus its own BI. So if it exceeds AI, then the answer is no. And otherwise, if nothing happens, the answer is yes. And basically, it's not hard to see why it's true. Like, we have to sort them in this order just because when we have at least 3 minions, it is possible that all buffs go somewhere else. Like if you have some pair of minions, well, n equals 3 may be a bit different, but overall, like starting from 4 at least, for any 2 minions, it could be that all buffs go to some other places. So it means that we should order them by AI. Like we cannot ignore this part. We have to order them this way. And then this is actually like ordering by BI is only needed in one case. When we have only one buffer, only one minion who is buffing. So let's say we have, like in the example again, right? 10, 0, 7, 0, and 7, 3. Like here, the answer is yes. And that's because like the 3 can go here or here, and that's fine with us. But if we actually switch these two minions, then it could be their own ordering. So it's only needed in this case. Okay, so like just you can do it in n square, you can do it in n log n, whatever you prefer. Okay, that was problem A. It was kind of the warm-up problem for you in today's contest. It was also a warm-up problem for me in this analysis. Let's move on to the next problem. I guess just start a new page. So problem B was already harder, of course. Basically, we had some items. Each item was like a vector of integers of the same length. And we had some pointer. And we also had some set of like active positions, so-called like filters, which mean that this value should be equal to some value. Like we know when we stand at some item and we have some set of active conditions, we know that the values in these positions should be exactly the values from this item, because the item satisfies all the conditions at any point, right? And we can do some operations. We can do right, left, which goes to the next item with the same values in these positions, or maybe the previous item in cyclic order. So we can go like here with right, we can go here with left, or we can add filters or remove filters. If we add the filter, we just remove something from a position. And if we add the filter, we go to the next item, which will satisfy the new condition, okay? So like that was mostly the problem statement, but the solution is kind of like, if you just don't think about the complexity of the solution, you can just see that it's just kind of breadth first search, for example. That's what one thing you can do, right? The thing is the state at every point, the state of our like structure can be given by just two integers, I and j. I is the current item, and j is the mask of filters. So this is at most n, and this is at most 2 to m, right? And we can just, to solve the problem, we can just choose the first item, the item we start at, and we can just do BFS, like on these states, at every point, we just loop over the next like operation we do transitions, and so on. Like the only question is whether it's fast enough. Let's see. So first of all, what about the left and right operations? We can actually pre-compute them easily, and that will be efficient. We just brute force, like before any BFS, we just do like we try every mask of filters, and yeah, let's say we have some items with equal values in those filters and items with non-equal values. We can just like split the items into equivalence classes based on the values in the chosen positions, and you can just like pre-compute the actual next and previous, right and left. So for this item, the right one will be this one, the right one will be this one, the right one will be this one. The same goes for going left, and here this item points in this item, and this item points for this item at this item. So that's just what happens when, like for each mask, that's what we built. Like we built a structure like this. For each item, we find the previous and the next one. So that's easy. We can now make transitions in our BFS in just constant time. Those that regard the left and right buttons. What next? Next, there is also the remove filter button, right? We can take any filter and remove it, like I said. And obviously, we just go to the state with the same item and a different mask, right? And again, like these transitions can be just done in constant time, right? Like there is only, okay, m at most m transitions of this kind from any state, right? So that's also easy. The difficult transitions are when we want to add some filter, we don't actually know which filter we want to add. Like we can try to choose a new position. Let's say we want to add the filter in this position. But the thing is, we also can change, we can choose the value in this position, and it will influence where our pointer will go. So it turns out that we actually can have a lot of transitions of this kind from any state. And in particular, if let's say our matrix of items is like this, 1, 2, 3, 4, 5. Okay, so like the first, let's say 4 parameters have the same values for any item, and the last parameter is unique for any item. Then it turns out that we can just make a transition, like if our mask does not include the last parameter, then we can make a transition to any item, right? We can choose the last parameter to be equal to anything, and we can just move to any item. So we can have a linear number of transitions here. And the question is whether we can make them quickly. So one way to do that could be to use, for example, bit set, or we can just like pre-compute the bit set of possible transitions of this kind from any pair ij, and we also maintain a bit set of unvisited states in the BFS. We just end them and find like all the 1 bits in them. And yeah, let's actually write down some complexities now, like time complexities. So if we just do it in straightforward way, without bit sets, we will have, so n is, we choose the first item, the starting item, then we do BFS, which has n times 2 to m states, right? This is states. States, this is start. Okay, now we can choose basically any new filter, which is like adding a new filter is the most difficult operation. And we can have n transitions, right? So this complexity n cubed times 2 to m times m, which is, it's a bit too much. You could probably get it under the time limit if you tried really hard. Like if you really wanted to, you maybe could do that. If you use bit sets, you also divide that all by the machine word size, which is like 64 or 32, I guess 64 in this year. That is probably fast enough. And anyway, the intended solution is a bit different. It has another idea, which allows to make transitions quickly. And the idea is that we actually want to go backwards, not forward. We don't want to find the distances from one item to all the others. We want to choose the final item, the finishing item, and find the total, like the distance from every other item to this item. And if we do breadth first search this way, in reverse, we can actually finish faster. I mean, not finish faster, but like be more efficient. How can we do that? So let's see. First of all, what are the reverse of left and right? They are just right and left. So we don't need to do anything in this part. Now, the reverse of removing a filter is just adding a filter. But this time we add a filter and we just like choose a filter. We don't move the pointer anywhere, right? So now adding a filter becomes an easy operation. We just loop over the filter, but we don't move the pointer. We add it, but we don't move anywhere. And the more difficult operation is removing a filter. So let's see. Removing a filter, okay, a filter in reverse. So, okay, let's say we have some item and we have some values like the active values, and let's say like this, and let's say like, I don't know, blue, like equal colors are equal values, okay? So yeah, let's say we had this item and we want to remove the filter corresponding to the last column. Where could we go from? Like when we go not in reverse, from which items could we go by adding this filter? Okay, let's say here we also had one more item, okay? Yeah, so the thing is, like what I claim is that we can go from this item. If we had just this mask, we could just add a new filter, which is like red for the last column, and we could go to our current item, okay? Similar, we can take this item, and if we add a new filter that the last column is equal to the red color, then you can just go here. Okay. Okay, let's go here. Okay, and now for this item, we cannot actually go from this item to this item by adding this filter. I mean, yeah, not like this, but let's say, yeah, we had this state. If we just add a new filter to the last column equal to the red value color, the transition will be just to this state, right? So what it means is that we just go backwards in the list of states with the same values in all the active columns, except the one that we want to remove. And we just go there until we hit an item, which is also equal to us in this column, like the last column we want to remove, okay? Okay, maybe that's a bit hard to grasp, but hopefully not. So now how do we optimize it actually this time, right? We can use some kind of a set, maybe C++ set, but even easier, you can use disjoint set union. So for each mask of, for each filter mask, we will have a disjoint set union on all items. And then when we visit some item in our BFS, then we like remove this item from the DSU for this mask, like not actually remove, but we make its parent the previous item with the same values. Okay, so like we want to find, like the thing is, we want to find the closest item to the left of our current item, which satisfies some conditions, like has these values in this mask, but is not visited in the BFS yet, okay? And to do that, we can just use a DSU, and DSU just allows us to kind of remove any element and then find the previous non-removed element, okay? And so that's just what we do. When we put a new thing into BFS, we remove it from DSU. When we want to make transitions, we go by the DSU until we encounter an item like this, which also matches in the column we are removing. And then we stop. And this way, we don't make any extra transitions, like any step in the DSU actually gives us a new state in the BFS. So the complexity becomes just n squared times 2 to m times, well, some log n. Like if we just use, let's say, no rank heuristics, but just the path compression, we will have log n. Okay, that was it. That was problem B. The idea, at least, that I had in mind for it, that going backwards is actually helpful and allows us to make transitions faster. And I think let's go forward to problem C. If you have any questions, just post them in the chat. I'm looking at it. So problem C. Yeah, we had some number line. We had some 3 points. And we had a process of k seconds. And every second, we chose a random point, and it moved by 1 to the left or by 1 to the right with probabilities, okay, 1 minus p and p, I guess, but it doesn't matter. And we repeated that k times, and after all the points like moved somewhere, and let's say this point finished here, this point finished here, this point finished here, we wanted to know the distance between 2 farthest points in the result. Like we want to know the expectation of this length. Okay, so why do we have 3 points? How is that important? Like we want to know the expectation of the minimum and the maximum, for example. That's one thing we could do because length is equal to maximum minus minimum. We know that expectation is linear. So expectation of length is equal to expectation of maximum minus expectation of minimum. And that's one way to go about the problem. but without any further observations, it's pretty tough to calculate the expectation of maximum minimum. Actually, I think it will be possible, but we'll talk about that later. But the idea that helps a lot in this problem is that instead of looking at 3 points, we can just look at 2 points at a time. And why is that? Because actually the expectation of the length is equal to half of the expected distance between every pair of points like len is the total segment we need to cover all the points, and the expectation of distance between 2 points is just the expectation distance between 2 points. And the thing is, we can just add them up, the distances between the points, take a half of that, and that will be the answer. Again, because the expectation is linear. It's easy to see, like if we take a look at these 3 points, we have the distance between 2 points, distance between 2 points, and then the distance between like the last 2 points, right? If we add all these distances, we will just get twice the length of the segment we are looking for. That's why the formula is true. And now, what do we do about 2 points? Like we can just now go and find the expectation of distance between 2 points. And that's actually easier. So let's say that we have some random variable d, which is initially like equal to the difference of coordinates of 2 points, actually the sign difference. So it will be negative if point 1 is to the left of point 2. It will be positive if it's the other case. So how does this distance change with time? In 1 second, what could happen? With probability 1/3, distance just doesn't change, because the person that is chosen this second could be the 3rd person, the one we are not looking at right now. So with 1/3, the distance doesn't change. Then, if person 2 goes to the if person 1 goes to the right, this happens with probability p/3. Or if person 2 goes to the left, which happens with probability 1 minus p/3, the distance actually increases by 1. Okay, so if x1 increases or x2 decreases by 1, distance increases by 1. And we can see that this is actually also equal to 1/3. And the last transition is if x1 decreases or x2 increases, which also happens with probability 1 minus p/3 plus p/3, which is actually also 1/3, the distance becomes d-1, right? All right. So now we need to simulate k seconds of this process and find the expectation of modulo. I mean, the expectation of the absolute value of d. Okay. And how do we do that? It's actually easy to see. We can just have a polynomial, which is 1 plus, let's say 1/3 plus 1/3 x plus 1/3 x squared, polynomial of x. And if we take this polynomial to the k's power and take the coefficient of x to I, this will be equal to the probability that distance final is equal to the initial distance plus I well, minus k, I guess. Okay. So like we have three options, like these three options, if we take a look at the exponent, they are 0, 1, and 2, right? So like if we say that like it's not minus 1, 0, 1, but 0, 1, 2, it doesn't change anything. It just shifts everything by k eventually, right? So what we do is we just build this polynomial, we take it to the k's power, and we take its coefficients and use them to find the probability that the final distance is equal to every value, and just sum these probabilities weighted by the values of the absolute values, and we will get like the expectation of the absolute value. Okay. Yeah. So that's like the solution to the problem. If you have any questions, ask them. And one interesting thing actually in this solution, is that you can see that actually p doesn't matter at all. Like this is 1/3, this is 1/3, and then we don't have the probability of going to the left or to the right anywhere in the solution. So with any value of p, the answer is always the same. I wonder if there is an easy argument to show that, like not going through the whole solution to explain that, but maybe not even going to the pairs of points instead of the triple. But anyway, like that's just an interesting fact that is worth mentioning. And using that fact, you can actually assume that everyone goes to the right instead of choosing the random direction, right? Because since the answer doesn't matter, like doesn't depend on p, we can just assume that p is equal to 1, that we always go to the right. And this way the problems becomes easier, and actually it becomes possible to solve it faster, I guess, like or without like any polynomials. And like I said, we can actually go back to the expectation of maximum and minimum, and that's actually doable in linear time with some prefix sums of binomial coefficients. So yeah, that's another interesting thing about this problem. Okay, that's problem C. If there are no questions, let's go to problem D. Okay, in this problem, we had to build a graph with n vertices. We wanted to have some vertices to have degree equal to 1. The other vertices had to have degree greater than 1. And we wanted the graph to have diameter at most 2, so that any 2 points, any 2 vertices can be reachable from each other in at most 2 steps. And we wanted to minimize the number of edges in the graph. So yeah, this problem has 2 major like cases. K is the number of degree 1 vertices, and the cases are k equals 0 and k greater than 0. They are actually a bit different, and now we'll talk about why. So let's take a look at the easier case of k positive. So it means that we have some vertices with degree equal to 1. So it means that they all have to be connected to some vertices, like in the other part, right? Because we have at least 3 vertices in the graph. And also it's easy to see that like all of them have to be connected to the same vertex, because otherwise the distance between 2 such vertices of degree 1 will be greater than 2. And moreover, since the distance from every vertex of degree 1 has to be at most 2 to any vertex in the graph, and each of them is connected to just 1 vertex, it follows that all the other vertices in the graph have to be connected to this main vertex. So we will have a vertex of degree n minus 1. And that's important, like we must have such a vertex. All the leaves degree 1 vertices will be connected to this vertex. And maybe something else, right? Since all the other vertices have to have degree greater than 1, we also have to connect them like to increase their degree. So for example, in this case, this is the solution to n equals to 1, 2, 3, 4, 5, 6, 7, and k equals 2. So this is the actual solution. Once again, like the solution is we just connect the k vertices to one main vertex, which is blue in this picture. And then we connect this blue vertex to every other vertex. And then we split the remaining vertices into pairs and connect them. And if we have some extra vertex, let's say, we can just connect it to like any vertex, like because of parity, it's okay to have like one more edge. Yeah. And then there are some cases when it's actually impossible, right? One case is k equals n, it's impossible. Just because like all vertices cannot have degree 1, it won't be connected in this case. And actually another case when it's impossible is when k equals n minus 2, because what it means is that we have some degree 1 vertices, they are all connected to one vertex, but in this part overall, we only have 2 vertices. We can connect them, but we cannot escape the fact that this vertex will have degree 1. So when we have n minus 2 vertices of degree 1, they are all connected to the same vertex. We must have degree 1 in the last vertex, in the remaining vertex as well, which we must not have. So we have 2 impossible cases. We have a simple construction, and it's kind of obvious why it works when k is positive. And let's go to the second case, which is k is equal to 0. And a tempting idea is to like generalize the solution, kind of, and just say that we always have a vertex still, which is connected to every other vertex, like this, okay? And if you have such a vertex, then again, it's easy to build the optimal answer in this case, which is just like split the vertices into pairs, maybe add an extra edge if you have an odd number of vertices except this one. And like just say that this is the answer. Like, for example, maybe you have some more vertices like this, okay? So that's one way to build the graph, which is which works, but is it optimal? And let's try to prove that it's optimal, right? When I was actually coming up with this problem, I figured out like this construction, which is easy, and then I just tried to prove the solution. And in the process of proving it, I actually noticed something like that we cannot actually prove it. And it turns out that this leads to some corner cases, which most of you, I guess, encountered, at least those who tried this problem. So how do we try to prove it? Okay, so once again, the case when one vertex has degree n minus 1 is covered, right? We have considered this case, like we have the optimal solution for this case. What happens in the other case when we don't have any vertex of degree n minus 1? First of all, let's consider this case, okay? For simplicity, let's take, let's take the case of an odd number of vertices first, and the case of even is similar, just like consider one case, okay? So let's say n is equal to 2 times t plus 1 for some t, okay? And let's then erase this thing. Okay, so if we have n equal to 2t plus 1, then how many edges do we have in this construction on the left? Well, we have t triangles, right? We have one vertex in the middle. We have t pairs of vertices. Each pair gives us a triangle. So it means that we have 3 times t edges in this case. And the question is, can we do better? And again, here, I thought about vertices of degree 2, right? Like we often, like we need to have vertices of degree 2. For example, let's say that, consider the case that all vertices have degree at least 3. What happens in this case? In this case, the number of edges is at least 3n over 2, right? And if we like substitute 2t plus 1, we get 3, I guess 3t plus something, right? Plus 1/2, whatever. Like we don't get better than 3t, and we can reach 3t. So it means that the case of all vertices of degree at least 3 is not interesting. Like it doesn't give us a better solution. But we have some, okay, let's say the other cases, we have some vertex of degree 2. Okay, let's take a look. We have some vertex of degree 2. It has 2 neighbors. Now, the distance from this vertex to any other vertex should not exceed 2. So it means that every other vertex of the graph has to be connected either to one of our neighbors or the other one, right? So every other vertex of the graph has to be here or here, because the distance from this vertex, the root, has to be at most 2. Okay, let's say that this part has A vertices, this part has B vertices. And then what is this, like the number of the smallest number of edges we can have in this construction? Okay, so we have okay, these 2 edges first. Then we have A edges here. We have B edges here. So we have A plus B. And then we have A plus B vertices of degree 1, which must have degree at least 2. So we need at least A plus B, okay, over 2 rounded up edges to connect something like inside this, like maybe between the parts, maybe inside the parts, but we need at least this number of edges. And let's again like substitute something. Like we know that actually A plus B is equal to, okay, so we had 2t plus 1 there. That's everything but 3 vertices, so it's 2t minus 2. So it follows that M is at least 2 plus 2t minus 2 plus 2t minus 2 over 2 rounded up. And that's actually equal to 3t minus 1, okay? And why is that important, right? That's important because this value, 3t minus 1, is actually smaller than this value by 1, but it's smaller. So it means that we could have a solution with 1 less edge. And now the question is, like, can we actually have such a solution? And when we like try to consider some cases, we can figure out that actually that's not often the case. For example, if we have at least 2 vertices in both parts, like to actually get to the good case, like to actually have this exact number of edges, we have to just connect each vertex to one other vertex, right? So for example, here we could make one connection like this and one connection like this, and it's easy to see that this vertex will not have distance 2 to this vertex, right? So if we have 2 vertices from different parts which are not connected to each other, it doesn't work. Like similarly, if we just connect this and this, again, like this distance is just way too large, so it doesn't work. So it actually turns out that if we have at least 2 vertices here and at least 2 vertices here, it doesn't work. Like we cannot have diameter at most 2. And then we just consider the case when we have just 1 vertex in one part. Okay, we have 1 vertex here and we have some vertices here. Again, like if we just have this way and this way, like the distance from the lonely vertex of the left part to like not connected vertex from the right part is more than 2, like it's at least 3. So it turns out that when we have at least 1 here and at least 3 here. It's also like, okay, I mean exactly 1 here, let's say. And at least 3 here, it also doesn't work. Then you can also consider the case when we have 0 actually, but again, like it doesn't lead to anything good. And they're actually like the only cases when we get some meaningful graph are when we have just one vertex in both parts equal to 1, equal to 1. And in this case, we just make a new edge. And that's actually how the graph on 5 vertices looks like. And similarly, like I was talking about the odd case, and if we analyze the same for the even case, we get to the 1 and 2 case here. And like we can have edges like this and this, okay? And so for n equal to 6, we can have 7 edges, which is better than the 8 we get by the previous algorithm. And here for 5, we get 5. And also, yeah, in the case when one of the parts is empty, we will get the case of 4, okay? So n equals 4, m equals 4. All right, so if a vertex belongs to, okay. Yeah, let's see. Let's take a look at the questions. Yes, okay, so I'm claiming that these cases are the only cases that we need to worry about. What happens when one vertex belongs to both parts? Okay, I'll just consider the odd case, okay, like the even case is similar, just the odd case. When you have 2t+1 vertices, okay, for example, one vertex here, okay, so we have 2 vertices here and 2 vertices here. Yeah, like in this case, yeah, I mean, I'm considering 5. Whew. Okay, like if I want to consider 7 or more vertices, for example, then I need like 2 here, right? For example, like 2 here and 3 here, okay? Like maybe I have more, if I have a larger intersection, I guess it won't work. Okay, yeah, actually I have, we will get our boundary wrong then. Yeah, I mean the lower bound on the number of edges, right? That's what you're probably talking about. Yeah, okay. Yeah. Then a plus b is at least 2t minus 1. Yeah, okay, yeah. Actually, the last comment is what I like the most. Yeah, yeah. Thank you for saying that. That was probably what I was actually thinking. We don't need, if a vertex belongs to both parts, we actually don't care which part it belongs to. Let's just put every vertex into one of the parts, right? And if we actually put the vertex to the other part as well, then it just counts as an extra edge we added after we split the vertices into parts, okay? And yeah, the other comment which says that we will get the boundary wrong, like the number of edges will be too large, is also like also applies. That's also true. But we can just say that we put every vertex into one part because it has to belong to at least one part. Yeah, so, okay, that was like mostly almost the complete proof of why only these 3 cases on the screen are the you have 2 long paths then as well. Yeah, that's true. Okay, so that's why like we only have 3 special cases where we can do better than the construction from the above. And talking about like solving the problem in contest, you could actually like not prove anything like what I did. It's kind of long, right? It takes some time. It takes time on paper. So if you're using one computer, then it's maybe better. But like overall, you can just, when you get wrong answer on such a problem, you can just implement a brute force solution, which finds the best graphs for 5, 6, 7, 4 vertices. My brute force solution, which I implemented, it worked even up to 9 vertices, I think, maybe even 10. And you can just see like the cases where your solution is not better. And maybe if you hard code those cases, you just get accepted. That's like also a way to go about the problem. And that's generally fine. Like if you have some intuition that in the large end case, your solution is optimal, but maybe there are some small cases, you can just implement brute force, or you can also draw a case on paper. That's fine too. But anyway, I like this problem mostly because like there's some intuitive fact that you should have a vertex of degree n-1, which looks true. And then when you try to prove it, you actually find the small counter cases, which are the only counter cases. So that's that's my take about the problem. I guess we are done discussing problem G for now, and let's move on to problem E. Yeah, problem E. Problem E was about the cactus. As you might know, or maybe might not know, problems about cactuses or cacti, as people say, appear often on Northern Eurasia regional contests. That's like a long-term tradition, which like the first problem about cactus appeared more than 10 years ago, I'm not sure, and they appeared quite regularly. Not every year, but often that happened. And this time I came up with this problem, and I just didn't feel like proposing it to the Northern Eurasia finals, which is actually happening this year. I just decided to set it here, and I hope you enjoyed it. So what the problem was about, we have a cactus and we direct every edge. Now the question is how many pairs of vertices we have so that one vertex is reachable from the other one. In fact, you don't like, there are some techniques to work with cactuses, like you can do some DFS, you can like use the fact that you have at most one edge going up from some subtree. And I guess you can like solve this problem in different ways, but I will tell my solution, which I find kind of elegant. And yeah, I mean, many teams used it as well, but I think some teams did not, among those who solved it. So first of all, how do you solve the problem on a tree? Let's say we have some tree, and we again like direct every edge. How many pairs of vertices do we have in this tree? Actually, it's like the easiest solution to this problem, I think, is just not care about the tree at all. Only care that it is a directed graph. Also without cycles, right? It's actually a DAG. And what we can do is we can just build a topological sorting of this tree. I don't know, like this maybe. And now we can just do the usual like dynamic programming. For each vertex, count how many vertices are reachable from it. So like for this one, we have 1. For this one, we get 1 itself. For this one, we get 2, which is 1 plus 1. For this one, we get 3. For this one, we get 4. We just add all these values and we print it, right? Why it works? Because we have no cycles. So when we have some vertex and more than one edge going outside from it, the sets of vertices reachable via these two edges do not intersect, right? Because otherwise we would have some cycle. So it means that we can just use this dynamic programming. We won't have any intersections. We just add it and we get the answer, right? So that's as easy as it gets for a tree. And now what happens on a cactus? I claim that actually not much changes. We can kind of easily generalize. So one thing about cactuses, like the problem with cactuses, and is that we can have cycles. For example, here we could have an extra cycle like this. In the directed graph, this cycle could be a cycle or like not a cycle, right? What if it's a cycle? Then what we can do is we can just compress it into one vertex with, let's say, some weight equal to the number of vertices in this component, in this cycle, equal to 3 in this case. So we just compress all the cycles, or we can just say that we compress the strongly connected components, not cycles, in the directed graph, okay? So we just take all the strongly connected components, compress them. So each component has some weight now. And again, we do the same dynamic programming, like the one on the right, but we also take weights into account. Okay. So one thing that can happen is that we can have a cycle in the directed graph, right? We can handle that by compressing strongly connected components. What else can happen? The other thing that can happen is that we can have a cycle like this, like not a cycle, but it's not a directed cycle, but it still influences our dynamic programming. Why? Like I said, let's try to compute the number of vertices reachable from each vertex. So here we had 1, here we had 2, here we had 2, and here we have 2 plus 2 plus 1 plus 1, which is 5, right? If we just compute the dynamic programming values, as I said previously, we will get 5 here, which is 2 plus 2 plus 1 plus 2 plus 2 plus 1, just full stop. And it's 5, but obviously we have just 4 vertices. And why it happens? Because we counted this vertex twice. So let's see, if we have some vertex, we have some 2 edges going out from it. And let's say that the sets of reachable vertices via these edges intersect. It can only happen if we have some cycle in our undirected graph. And we can go by 2 arcs of this cycle from one vertex to another vertex, like in this case, right? So if we have some vertex which is reachable in both ways, it means that we have some cycle which is directed like this. We have just one vertex of degree 2. We have just one vertex of degree 0, and all the other vertices have degree 1. I mean, let's say out degree, okay? So one vertex has 2, one has 0, and the rest have 1. So if we have a cycle which satisfies this, it means that for this vertex, we will add the dp value of this vertex an extra time, and we have to just subtract it. So that's what we will do. First, the solution goes as follows. First, we compress all the strongly connected components, and then we identify all the cycles. And then if we have any cycle which goes like this, just memorize that we have to subtract the red dp value from the green dp value when we are calculating the green dp value. And we just memorize this, and then just we just do topological sorting, and we just do dp. So that's the solution I had in mind, which I think is the easiest in terms of like the black boxes we use. Like we still have to type some code to find the cycles, like undirected cycles in this case, and so on. But otherwise, we don't really have to handle this cactus in any special way. We just need to find the cycles, undirected cycles in the graph. Like we don't have to do any complicated DFS, that's what I mean. Okay, so that's problem E. If there are no questions about problem E, let's go to problem F. problem F was about what? What for cycles? I'm not sure about what this question means. Can you elaborate? Directed cycles. Yeah, okay. So directed cycles are handled by compression of strongly connected components in the first step. After we compress them, now we have some weighted vertices, not weights one, but something else. But now we don't have any directed cycles. Okay. Okay, just start over. What was problem F about? Actually, that's a good question. Okay, first occurrence, I see. So we had some famous binary string. Okay, yeah, I guess this one should be 1, 0, 0, 1, 0, 1, 1, 0, and so on. And we were given some substring. And the question was, where is the first occurrence of this substring in the string? So the problem was like, we were given two indices in the string. So the substring we are searching could be too long itself. Like it could be long. So we cannot just write it down and try to find it. Because I don't really know, like this is obviously not the first problem about this binary string in the world. However, I think the idea that we can find substrings inside the same string is kind of funny. Like that's why I thought this problem is worth setting up. Because if we were just given a string, maybe this problem is even well known. I don't know. But anyway, how do we handle this this case? We actually need to use some, like there are multiple approaches. As I looked at the codes of the participants, there are some more complicated or less complicated approaches, and I'll describe mine, which is pretty simple, I think. So we need to take some definition of the string because there are many of them, right? In the problem statement, you had something like 0 if okay, pop count of n is even and 1 otherwise, right? And you could maybe work with this definition and go ahead, but a good definition to work with is the like kind of recursive definition. The idea is that if we take the string t and then we replace all zeros with 0 ones and all ones with 1 zeros, we again get the string t. Right. That's easy to see. That's actually like, if we take a look at this condition, it's just multiplying every number by 2 and adding 0, adding 1, like kind of adding a new lowest bit to every binary number. And so why is this useful to us? Because we just want to go kind of down. We want to divide the length of the substring we are looking for by 2. And we can kind of do that. Let's take a look like at some general substring, like in general case. Let's say we want to find this string in our long string, okay? There are two ways, like there are two different parities the string can start at. If it starts like at an even index, then we should have like all these digits split into pairs of consecutive digits. And in each pair, we should have either 0, 1 or 1, 0. But we cannot actually, like if some pair is 0, 0 or 1, 1, then we cannot split this way, right? And Then there is the other case. If we start at some odd position, then we split like this, like with different shift. And again, on each pair, we should have 1, 0 or 0, 1. Otherwise, we cannot take this parity of the starting index of our substring. And so the thing is, let's say we are given the string itself. We can find out what parities are possible. In this case, the red parity, which is the even, is not possible because we have 0, 0, but the odd parity is possible. Then we compress the string. We compress it into, okay, so here we kind of have 1, 0, right? Because 0, so before it should be 1. Here we should like this. So we compress it into 1, 1, 0, 0, right? Because this one is 1, this one is 1, this is 0, this is 0. So we compress it like this. And now let's find this string in the previous iteration of our like replacement process. Okay, like let's find the shorter substring in the long string, in the infinite string. And then after we do the replacement with this short substring, we actually get the initial substring we were looking for. So let's, instead of looking for 0, 1, 0, 0, 1, 0, let's look for 1, 1, 0, 0. When we find its first occurrence, we just multiply it by 2, kind of, like actually multiply it by 2. We add the parity if it's 1, which we should do in this case. And that's it, like that's the whole solution, right? So we can just divide the length of the string by 2 until we actually get to some short string. Let's now talk about what parities could work for us. For example, okay, like my claim is that if we are looking for some string like 0, 1, 0, 0, 1, 0 again, if the string is long enough, where long enough is at least 4 characters, I think, maybe 5, then only one parity can work. And if only one parity can work, we don't need to branch in our process of finding the substring. We just go to the only case which could work. Why only one parity works? Let's say we have some, okay, longer string. So first we, okay, once again, we split into pairs like this. So for this parity to work, we need characters in the same pair to not be equal. Okay, so this pair should not be equal, this pair should not be equal, this pair should not be equal. Then this parity, the red parity, could work. Now take a look at the blue parity. Again, each pair should be not equal. So this pair should not be equal, this pair should not be equal, this pair should not be equal. So if both parities can work, it means that our string is actually 0, 1, 0, 1, 0, 1, 0, or maybe it starts with 1, but like it has to just be zeros and ones repeated, right? And what happens when we compress our string? When we compress it in the red way, we get, okay, 0, 1 results in 0, 0, 1 results in 0, 0, 1 results in 0, 0 results in 0. When we compress in the blue way, 1, 0 results in 1, 1, 1, 1. That's what we actually get. And the thing is that in our string, there are no blocks of zeros of lengths more than 2, because every 0 has a 1 next to it somewhere. A 0 can't have 2 zeros next to it. And the same goes for 1s. So if both parities work and the string is long enough, I think at least 4 characters, we cannot, like if both parities work, then the string is actually nowhere in the big string. So there are no occurrences in this big string. And if we need to have at least one occurrence, then both parities cannot work, which is like the same but inverse. It means only one parity can work, and we can work with that now to solve the problem. Returning to the actual problem, we had some L and R given, which are the indices in the big string, only one parity works, and we obviously know which one works, right? Because we just take the parity of L, and like this one obviously works always. So the solution to the problem becomes like this. Let's say we have f of L and R, which is the function to solve the problem for some substring. So if the string is short enough, I don't know, some constant, we can just, I don't know, just find it. Like if the string is short, we can just find it in some first characters of the string. And otherwise, f of LR is actually equal to f of L over 2, R over 2, and plus the parity. The parity is L modulo 2. Okay. So if you followed all of my like explanations here about compressing the string and dividing its length by 2, that's basically what we do here. If you have a string from L to R, we can compress it into a string from L over 2 to R over 2, both rounded down. We can find it in the original string, and we just add the parity to account for the parity on this step. Okay. And so that's actually the whole solution. Like just find it is just like 3-line build both. You can just build both strings and just try to find it like using string find. Otherwise, you just call a different divide the length by 2 and recurs. Okay, so that's the solution to the problem. It works in log of R time. Any questions about this solution? Okay, hopefully that was clear enough. Let's move on to problem G. What was problem G about? It was about longest common subsequences. Yeah, we have two sequences, A and B, and we need to find the sum over all x of longest common subsequence of A with all elements shifted by x and B. So let's, one important feature of this problem is that we had limited memory. We had plenty of time. It was still not enough for everyone, but it was mostly enough. And we had we were pretty tight on memory. We could not even have a matrix of size n times m. But anyway, let's take a look at the matrix, kind of. And let's say we have some x. Let's say we have chosen some value of x. In the matrix, let's kind of like mark some cells. I don't know, in all such rows and columns I and j, such that ai plus x is equal to bj. Okay, so we just mark all such cells, and now if we mark them, how do we find the longest common subsequence of a plus x and b? We just need to find some like subset of these cells which goes strictly to the right bottom. Like if I increases this way, j increases this way, we just need to find some like path which goes from top left to bottom right. I mean, don't look at my hand, and visits as many of these cells as possible. And it cannot visit two cells in the same row or column. So how can we also formulate that in a bit different way without the matrix? Let's write down all pairs which like satisfy this condition. I I1, J1, I2, J2, okay, whatever, I3, J3, so on, IK, JK. Like I remind you that like we have chosen some value of X and we are now working with this value of X. So we have some pairs which satisfy this condition. We need to choose some pairs which like go like so that I increases in these pairs and J increases in these pairs too. So I claim the following, which will be useful for us. Okay, claim, I don't know. Let's sort the things in increasing order of I, like the pairs. And if I is equal, in decreasing order of J. Then the claim is that longest common subsequence of A plus X and B is equal to longest increasing subsequence of J1, J2, so on, JK. Okay. Yeah, that's kind of easy to see, right? If we have all I's distinct, let's say all I1, I2, I3, and so on, all of them are distinct. We just sort by them, and we want to find some increasing subsequence of J's. It will be like what we are looking for. And if some I's are equal, then we sort them in decreasing order so that we don't take more than one pair with the same I in our increasing subsequence. Okay. So that's important. Like that's why we sort by J in decreasing order after we sort by I increasing order. And now, if we have this knowledge, what can we do? Another thing which I didn't mention yet, but which is important, is that any pair ij is only used for one x, right? Like if I have some I and j, if I want to match ai into bj, I need to have x to be exactly equal to bj minus ai. So any cell in the matrix, so like, or any pair of ij can only be used at most once for one value of x. So a solution which would use a lot of memory but would work in n square log n time would be just to take all pairs ij, classify them by the differences, like the x's. For each x, write down all the pairs, sort them by I and then by j, find the longest increasing subsequence, sum all their lengths, print the answer. That would be it. And since we have limited memory, we cannot take all the pairs and sort them. But we can actually just kind of generate them on the fly. And actually, we can even generate them on the fly in the required order, in increasing I, like increasing x. Like let's generate all the, like, let's say tuples xij in increasing order of x, in increasing order of I, and then decreasing order of j. And we can actually do that. Let's like kind of take a look at the matrix where we again have, okay, rows a to n. So like we have a1, a2, an here, okay? And here we have b prime 1, b prime 2, b prime m. Okay. It's not maybe clear in the picture, but let's reorder the columns so that the values of b are increasing or non-decreasing, more to be precise. And let's write down like the differences: b1, b prime 1 minus b1 here, b prime 2 minus b minus a1 here. So like in each cell of the matrix, we write down the difference between the corresponding b and I, b and a. And now the idea is that this, like, we want to order the elements of this matrix, right? Like each element of this matrix is some difference of B and A, and we want to sort them all. But if we reorder the values of B in increasing order, now every row will also be increasing. And that's a useful property because, for example, if we want to take the minimum of the whole matrix, we know that it always belongs like to the first column. The minimum is always here. The second biggest value is like either in the first column or it is to the right of the minimum, and so on. So what we will do is we will take all the first elements of this, like we will take the elements of the first column only and put them all into some priority queue. It could be like a heap, a set, whatever. And we will just take the smallest element every time. It will be the next like difference we are interested in. And after we take some element of the matrix, we put the next element in the same row back to the priority queue. Like we have a pointer in each row. And when we get some value from the queue, we just move the pointer, like advance it to the next position and put the new element into the queue. This way, we always have only a linear number of elements in the queue at every moment, and we can sort all the differences in n square log n time. And what remains in the solution, actually not much, is that in each row, we like in priority, I said priority heap, I meant priority queue, yeah. So in the priority queue, we will have pairs like xi sorted by like, again, increasing order of x and then increasing order of I. And then in the columns, we also need to actually sort them by B, like I said, but if the B's are equal, we sort them in decreasing order of the index, okay? So that if we take the elements from the priority queue, we actually get them in this order, which I mentioned, which we actually want. Okay, so we can force this order. And now the question is, after we force it, what do we do? And the answer is that we can just use any kind of online longest increasing subsequence algorithm. Like what I mean by online, we have some elements one by one. There are two main algorithms for that. One algorithm is just DP with some binary index tree, I don't know, Fenwick tree, segment tree. We can use that. When we get some new value, we get some maximum of our DP on prefix, and we update some new cell. We need to clear them between different values of x, so we can, for example, save all the used cells and then clear them at some points. And okay, that's one thing. And another algorithm is like lower bounds, like binary searches in some array. And this is even easier. Like we can actually do that. When we get a new element, we just do a binary search in some array, put it there. Like hopefully you know the second algorithm as well for the longest increasing subsequence. But both of them work here, and both of them use a linear amount of memory because the length of the longest increasing subsequence is at most n, and like the segment tree in the first case is of size n as well. So this way we get to the n square log n time and linear space. That was problem G. Any questions about it? Okay. Problem H. We had some points. We drew some angles. And we wanted them to not intersect, like the interiors of the angles, we wanted them to not intersect. We were given all the values of the angles. The points were on the same line, which is important. And we want to know the expected, actually the probability that no two angles intersect. So this problem was pretty hard. I guess I will not describe it in too much detail, but I will say the main ideas. So for each angle, we choose like the main direction, okay? Like, I don't know, we choose some direction for each angle, okay? And the angle just goes in counterclockwise from this direction. This direction is chosen uniformly at random, like what's written in the problem statement. There are kind of two cases for each point. Actually, it also only applies to the points in the, like not the first, not the last point, but each of the other points, it should always be the, like the angle from this point should always be directed either like up or down. It cannot be directed like this, because we will always intersect the angles from the points to the left of it or to the right of it. So like for each point except the first and last one, we should direct it to the top or to the bottom, the angle from this point. Okay, let's say that we choose for each point whether the angle goes up or down. And now let's forget about the first and last point for now. Let's say that we have some set of points from which the angle, okay, that's not great. Like, okay, so we have chosen some subset of points from which the angle goes up, and from the others the angle goes down, but for now we don't care about those. Okay, so now the question is, if we direct all the angles this way, what is the probability that no two angles intersect? And we know their measures here. And like, actually not the probability kind of, but like if we consider the, I don't know, the hypercube from 0 to 360 degrees in n dimensions, we kind of want to know which portion of this cube gives us non-intersecting angles in the top half plane. And it turns out like that this like volume of this portion is 180 degrees minus AI minus A2 minus so on minus A I know K, which are like 1/8 A1 AK. Okay, so we take this, we take it to the k's power, and we divide it by k factorial. And yeah, I guess we also divide by 360 to k. So like, or if we just want to calculate the volume of this part, like this is the actual volume of the part. Yeah, I will not explain this formula in detail, but you can check it yourself. So now, what do? We do that like for the top half plane, we know this formula, and for the bottom half plane, we can also find like a similar formula, like it will be just the same. And if we were not allowed to actually like go to the left or to the right from the first or last point, what we could do is just decide for each point where it goes, take this value, multiply it for the top and the bottom, add it by all, like add it over all ways to distribute the angles to the top or to the bottom, and that would just be the answer. Because of like the ability of the angles from the first and last point to go somewhere else, it's a bit more complicated. So like, once again, okay, let's say this is B1 and so on, BT. So the formula is this multiplied by 180 minus B1 minus B2 minus bt to the power of t over t factorial. And let's say that we have, okay, so let's say that we have some angles like this. Oops. And now we also have an angle from the first point, which goes strictly to the left. Yeah, low battery. I have to finish soon, but I will finish soon. Okay, like this. Okay. I will learn how to use it. Yeah, so we have an angle which goes like this. And what actually happens in this case is that we just have less space at the top and less space at the bottom. And so let's say that this angle is, I know, C0. What we actually want to find in this case, if we decide that the angle from the first point goes to the left, is we want to find the integral actually from 0 to C0. And here it will be 180 minus A1 minus AK minus X to the power of K over K factorial times, similarly, 180 minus B1 minus so on minus BT minus C0 minus X to T divided by T factorial D, okay, dx. So I claim that we are interested in this integral over X from 0 to C0. Like we can rotate this angle like in different ways, and it will take some angle X from the bottom and then the rest from the top. So we want to know this. And how do we do that? We can just find this polynomial and just integrate it as usual, and just like, since it's a definite integral, we can just plug in the C0 and 0 and take it. Like we can just compute it. And two more things that I did not mention. One thing is that I said that we decide for each angle whether it goes top or bottom. We cannot do it in like 2 to n, but we can do some kind of knapsack DP, because we are only interested in how many angles go to the top and what is their total degree amount. So we can just do some knapsack DP instead of brute forcing, and just like batch all the cases with the same number of angles and the same total angle going to the same side. And like, yeah, the other thing is that like this is one case when we have just one angle from the first point going to the left. There is the case when the angle from the last point goes to the right, and the case when both of them go to the left and the right respectively. And in this case, we will have two variables, let's say X and Y, and we'll have kind of a double integral over X from 0 to C0 over Y from 0 to C1. And we can like replace X plus Y by some variable and turn it into a single integral or something else. Like, I guess I will leave it as an exercise to the listener from here. And I'll say about the complexity. In my case, the complexity was m to the 4th power, where m is, well, I guess 180, we can say, kind of like the maximum degree. You can also use fast Fourier transform to get to m cube log m if you really want to, but m to 4 was fast enough. M to 4 because we need to loop over how many angles go up, what is the total value of these angles, that's m squared, and then we get two linear polynomials which we have to multiply, and both of them have degree m, so it's an additional m squared resulting in m to 4. Or if we multiply them quickly, we get to m cube log m. That's it for problem H. Problem I. In problem I, we had some algorithm to find this kind of the smallest like the smallest rotation of a permutation, the smallest in lexicographic sense. So we take the first element, and then we take the second element. If it's smaller, then we rotate. Then we take the third element. If it's smaller, then we rotate, and so on. And the question is how many permutations this algorithm doesn't work. Like the problem with this algorithm is that we rotate every time. Instead of just finding the minimal element and then rotating once, we rotate every time. And it means that our pointer might miss some elements. And that's the problem. So the solution to this problem, okay, so one brute force solution we can think of is just try all n factorial permutations. That's obviously too slow. We can do better if we just brute force on the condition in the algorithm. Like we have, the algorithm goes like this. For I from 2 to n, if AI is smaller than A1, then, okay, A is assigned, okay, AI plus 1, so on, AN, A1, so on. Okay, so that's the algorithm. So let's brute force over which of these conditions are true, like result in true, and which of them result in false. And so we only have 2 to n minus 1 options here. What can happen here? And so that's one way, like we can brute force which conditions are true. Oh, sorry, I need to take a 10-second break. Sorry, I'm back. Yeah, so we just brute force over what conditions are true and what are false. We get some comparisons of elements, and then we can count the permutations which satisfy all these conditions. Okay, how do we implement this kind of brute force? We can do it recursively. So we have some permutation at every moment. We have some element at the front, and the element at the front is always the smallest element we have seen so far, right? We have some other elements which we have compared our element to. We have some elements we have not compared it to, and we have some pointer at the current element, like the step of our algorithm, like which is actually I. Okay, so the state is described by actually the mask of elements that were compared to the first element and turned out to be bigger, because we always have the smallest seen element at the front and the pointer at some element. Okay, and the brute force solution, like the recursive backtracking solution, goes like this. We take the next, like the element the pointer is directed at. If it was not compared to the first element, then we will compare. We will branch here. We have two options. So one option is, is that this element will be greater than our minimum element. And it means that we will just mark it as, okay, so blue means that it was seen. So now we will mark it as seen, and we will just move the pointer to the next element. And the other case is that this element is smaller. Then we rotate our permutation. So now this element, okay, this was wrong. This element becomes the first actually, and so we rotate. So this actually, the first element which was red becomes blue, then goes the green, Yeah, then goes the blue, and the blue again. And again, the pointers in the last element. So how did I get this? Okay, so this element goes here, this element goes here, this element goes here, and so on. Okay, like I rotated it to make the first element, like the current element the first. And yeah, so that's how we proceed. In both cases, we multiply the number, multiplied the current number of permutations satisfying these conditions by something. Like I guess in this case we multiply it by 1, just because our element is the smallest of all the seen elements. And if the new element is not the smallest, then we multiply it by the number of blue elements, I think, +1 maybe. Yeah. So we just do this kind of backtracking. And it turns out that this backtracking is fast enough, actually, because it's not actually 2 to the power of n. Because sometimes we don't branch. Like I said, we only branch if the pointer is directed at a green element, which we have not seen. But if the pointer directs at a blue element, which we have seen, then since we have seen it, we know that it's not smaller than the first element. So we just don't branch, we just advance the pointer and move on. And that is like the main idea why this brute force solution is faster than 2 to n. It's still not super fast, but it's fast enough. Like it takes, I don't remember exactly, but less than 1 billion recursive calls for the largest case. So you can just pre-compute the answers. Like, yeah, the intended solution to this problem was pre-computation. Just because if I set the constraints low enough for brute force solutions to pass straight away, it would just be not like, maybe some slower solutions would pass using precomputation. So you can precompute the answers in several minutes. I don't know, like my Python solution worked in like 12 minutes. And if you use Java or Kotlin or C++ with big integers, you can even be faster than that. And also, yeah, that was it. I don't know. Any question about problem I? So like the idea of the problem was to just take the brute force and figure out that it's fast enough to actually compute all the answers because it has some pruning inside this. Okay, why not ask for the answer modulo P? What are the reasons to ask for the answer modulo P? I actually don't see it too clearly, so I guess we can discuss it later in the chat as well, but the answer is about n factorial, like it's of the order of n factorial. So for 42, it's not small, it doesn't fit into 128 bits, yeah. It doesn't fit there, but is that like, if int 128 overflows, is that the reason to ask the answer for the answer modulo something? Like one thing which actually I feel like is important is that I would personally want more like different languages to be used in general in competitive programming. Like a lot of people use C++ now, and it's kind of, okay, it's kind of a philosophical talk, which I should not be given, but I'll try to finish it in 1 minute. So like more and more people use C++, and problem setters like don't care too much about other languages when setting time limits. They just set it like 2x of their time, of their solution time. And this way, like people use other languages which are a bit slower, get time limit exceeded, get demotivated, switch to C++. And so like everyone switches to C++. Like lately we have some, I know, Rust alternative and something, but overall, one of the points of people who say like some people complain that the time limits are too strict, and other people reply, okay, why are you using the instrument which like it's your choice of instrument? You chose, let's say, Java, it's too slow, so you are to blame, like it's your problem. And I don't know, like let's say that in this problem, I just wanted to give a little bit like of something back to people who use C++, not C++, but like maybe Java or Kotlin or Python, so that they can just use the built-in von arithmetics. I don't know, like that's one thing. Like, I don't think the only, like, if the answer overflows, then we always should ask for it modulo p. Like, I don't think there's anything too bad if we ask for the exact answer. Like, given that you're pre-computing the answers anyway, I don't think that's a wrong decision. But we can discuss in the chat later as well. So that's my take. Let's go to the next problem. Battery is running low. Yes, I agree. We only have two problems left. Problem J, we had this equation. We were given K and we wanted to find the number of tuples NPM so that P is prime and this condition is true. So this is kind of a mess problem, as you can obviously tell. But anyway, like, I think it can be like used, even though maybe some people will not like it, some people will like it, and it's not exactly like a programming problem, but it needs some programming. So I think it's borderline fine. The important observation is that n square minus 1 is easily factorized. If we write it down as n square minus 1 equals k times p to m, we can write n minus 1 times n plus 1 equals to k times p to m. And in this case, what can we do? How can we use this? We should know that, okay, let's say that, consider the case of p greater than 2 first. It means, like, what I wanted to say actually is that the greatest common divisor of n minus 1 and n plus 1 is equal to 1 or 2 always, right? It means that both of them cannot be divisible by p when p is greater than 2 at the same time. So it means that n minus 1 is equal to, okay, n plus minus 1 is equal to p to m times some x, and n minus plus 1 is equal to k divided by x, right? So the idea is that all factors of p should go to 1 of n minus 1 and n plus 1. And we can just combine these two equations into x times p to m plus minus 2 is equal to k divided by x. And we can find that p to m should be equal to k over x plus minus 2 again divided by x, okay? And x in this case is some integer, because like it should be integer, right? So we can just try all divisors of k, like x should be a divisor of k over x should be an integer. We take this value, k over x plus minus 2, like two values actually, divided by x. If it, again, is divisible, if it's not divisible, we do nothing. If it is divisible, we get some candidate for p to m. We check if this number is actually a power of a prime, and we get some potential tuple which works for the conditions of the problem. And so the complexity of this is like kind of square root of k, because we just loop over x. Actually, x is not greater than square root of k, as you can see from here, like approximately. So then we need to check if the number is prime. Actually, like you need to take some root of the number we got, and then we need to check if that root is prime. We can do that in square root as well, actually. And if we sum the square roots of k over x squared, we get some square root of k times log k, right? So we can actually even afford checking each number in square root time without any fancy primality algorithms. And yeah, the second case was p equals 2, and it's similar, except that, let's say that one of the factors can go to, can go to a different number. So for example, it can be like this, equals to 2 times k over x. So yeah, once again, 2 to m minus 1 times x plus minus 2 equals to 2k over x. And it follows that 2 to m minus 2 is equal to k over x plus minus 1 actually over x. So in this case, we again loop over all x's, divisors of k. We add or subtract only 1, not 2, and we just check that we get a valid tuple. So the case of p equals 2 is not much different, except that we only check one, only have 1 here instead of 2. Yeah, that's problem J. And let's finish with problem K. In problem K, we had some binary string, we had some question marks. We knew the number of question marks that should be replaced with zeros and with ones, and we wanted to minimize the length of the longest block of equal digits in the resulting string. So the first idea in this problem, which is kind of what everyone used and probably like everyone who solved it used, and it's probably needed actually, is that we should do binary search on, okay, let's call it k, the length of the longest block. Okay, so we binary search on k, and we try to answer the question, can we replace the question marks with zeros and ones so that the longest block has length at most k? How do we answer this question? I claim that we can do the following. Try to replace question marks with zeros or ones so that all blocks have length at most k, and the number of ones, okay, let's say number of ones which we used to replace is minimized. Okay, so let's first find a way to replace the question marks to minimize the number of ones. And then do the same, okay, and maximize the number of ones. So instead of replacing the question marks with exactly some number of zeros and exactly some number of ones, we'll try to minimize number of ones and maximize number of ones. And then I claim that if minimum is, like if the value of b, which is number of question marks we need, which is number of ones we need from the question marks, lies in the interval between min and max, then it's b is also possible. Like if it lies outside of the interval, obviously it's not possible, right? Because even if the minimum is greater than b, that's not good. Even the maximum is lower than b, that's not good. But if b lies inside the interval, I claim that this is always possible to have an answer with b. And so if the problem was just asking us about the length of the block and not the string itself, that's what we could just do. We could just find minimum, find maximum, and check if b lies in this interval. one question which I didn't mention is how do we find like this number of ones? How do we minimize it? And I think that you can do it greedily. For example, you could just like try to put ones as rarely as possible, but not like try to satisfy the conditions. Because of the digits we already have in the string, it's a bit tricky actually, but that's doable as well. But what I did and what I kind of suggest for this sub problem is to use dynamic programming. We can just use, okay, for 2 and 3, we can just use dp of fi and 0, 1. Okay, let's say f min of 0, 1. We'll also have f max. And it means the smallest number of ones on the prefix of the string up to the ith character, so that si is equal to 1. Not 1, sorry. Si is equal to like 0 or 1. Like this is the same, okay? So the second parameter is the last character. And our dp looks like f min of I, for example, 0, low battery, but we are getting close as well, is equal to minimum of over j from I minus k to I minus 1, f minimum of j1, right? And f minimum of I1 is equal to minimum over j from I minus k to I minus 1, f minimum of j0 plus I minus j. So this is the formulas for f min and 0 of 0 and 1. And because of the characters we already have in the string, these limits are not actually correct. Sometimes we need to stop earlier. And the same here, like if we have some 0 in the string at some position between I minus k and I minus 1, we can take the rightmost such 0, and actually j should go up to this position. Like it cannot go farther just because we can't have all ones in this substring. Yeah, so if we just implement it in a straightforward way, we get n square, but we can use a minimum on a q, because this limit only increases as we increase I. We can use a q with the minimum operation, actually 2 q's for 1 and 0. And this way we calculate this dynamic programming in linear time. So we get a linear time for this part. With binary search outside, it's n log n overall. And now the last part about this problem is the claim that I can have an answer in the range. Okay. And this claim, and then also the proof of this claim, and also how to construct it, looks as follows. So we have some string. Let's look at both ways to replace the question marks to get minimum and to get maximum. So let's say that to get minimum, we replace the first question mark with 0, the second with 0, 1, 0, 1, 0, 0. Okay. And to get max, we get 1, 1, 1, 0, 1, 1, 1. I don't know. Okay, not good. Let's say 0, 1, 1. Okay. So we just find any way to get minimum and any way to get maximum. And the claim is that we can actually find some position in which we will just merge two parts of the answer, the prefix of some minimum answer and the suffix of some maximum answer. And this way we will get an answer like of any value between minimum and maximum. So it's easy to see that as we move this boundary, so we can start here. This way we get the maximum answer, right? As we move the boundary by 1, we can get the maximum, like the answer changes at most by 1, right? Because we removed the character from maximum and added the character from minimum. So the number of ones changes at most by 1 as we move this boundary. So it's easy to see that as we move it, we get every possible value between minimum and maximum. And the only actual question is, why do we get a valid answer by doing this? Why do we get a valid answer by merging some prefix and suffix? And indeed, it might not be the case that it's valid, but let's see, like we can actually make it valid. The idea is that we will only find for this boundary such that the bits next to the boundary are different. So for example, here 1 and 0 are different. So we will split here and this split works. Why does this split work for sure? Because in the big string, we have some like yellow 1 here and yellow 0 here, okay? So here we replaced something with this part, here we replaced something with this part, and here we had something, right? I know we had some digits. And the thing is that our string will not have any blocks too large. Like, why do I want the yellow digits to be different? That's actually important because if they are different, I can look at it this way. Since the minimum answer is correct, is valid, then on this prefix, I don't have any bad blocks, any blocks of length more than k. And since the maximum answer is correct, I don't have any bad blocks on this suffix as well. And if these digits are different, then I don't have any blocks which like belong to both prefix and suffix, but not to either of them. So the idea is that if the yellow digits are different, then I can be sure that after I merge two answers, the result will be correct. So the only question is whether we can actually find a boundary such that this happens. And the answer is yes, we can always find such a boundary. Basically because, like I said, we move the red boundary from left to right here. So we move the boundary from left to right. And let's draw some function of the number of ones. So it starts at max and it goes, I don't know, it goes like this. And it ends at min. Okay, so this is the function of the number of ones. And this one is cut position. Okay, so I get some function like this. And the function only changes by at most one between neighboring points. So let's say we want some value equal to b. Let's take any place where this function goes from the upper part, like the part above b, to the part below b. For example, we can find this part of the function graph. And let's find some cut position, maybe this one, maybe this one. We'll find one of them. One of them will be good for us. How to prove that? So here we have some value, okay? Since the last move was decreasing, it means that in minimum we had 0, and then maximum we had 1, since we decrease here. And since we decrease here, again, we have 0 in the minimum and 1 in the maximum. So there are two cases. If the decreases go next to each other, for example, if the graph just went through this value, we will have 0, 0, 1, 1. So if we cut here, this 0 is not equal to this one. And if they don't go next to each other, if we have some plateau, so like this, it means that we can have 0, 0, 1, 1, or something. We have equal digits in min and max. So we cannot split here. If we have different digits in the plateau, that we can just split between them. 0 and 1 are distinct, that's fine. And if we only have equal digits, if we have all zeros, we can split here. 0 and 1 are good. And if we have all ones, then we can split here because 0 and 1 are good. Phew, that was it. I don't know, like, I'm not sure that was really helpful, but anyway, that's the proof I have. Maybe there is something simpler. And it follows that we can construct a string this way, which has exactly the required number of ones. Okay, that was it. I proved the solution, the complexity is n log n. Do you have any questions about this problem or previous problems? We are at 3%, so we have enough time to even discuss your questions if you have any. There was a question why kilk in the name of the problem. Yes, that was the meme about the kilk is equal to count. And because I had a problem named kilk in my previous contest 2 years ago, it also was working with binary strings, and I wanted to minimize, again, the length of the longest block of equal digits. And in this problem, you had to count strings satisfying this property. In that problem, like last contest. In this problem, you have to construct a string, so you don't have to count, but the setting is quite similar. So that's why it's called kilk not, because you don't have to count, you have to construct. All right, I don't see any new questions in the chat, so thanks to everyone who is still here and watching. I hope you enjoyed this analysis and learned something new. I hope you enjoyed the contest as well, and I wish you good luck in all of your future endeavors. Thank you.